Okay, so I just wanted to make a quick video on this syllabus dot point for math methods. It says establish the formulas that the derivative of sine equals cos of x, and then the derivative of cos equals negative sine of x. Right, so we know these. We're aware of these formulas. They're on the formula sheet, so that's fine. By numerical estimations of the limits and informal proofs based on geometric constructions. That's something pretty interesting, right? And I'm pretty sure I skimmed over the past papers. There was nothing related to this whatsoever. So just in case, on the off chance that it's assessed tomorrow, I just wanted to make a quick video. So this informal proof I'll be demonstrating is not mine, right? It's from a website that I found. It's like I forgot the name of the person who demonstrated it, but I will link the website down below. Okay, so let's get straight into it. Okay. So you have the change, right? So you have the derivative of sine of x in terms of x. So we're deriving it in terms of x. You can change x to just be sine of theta, right? In the context of the unit circle, that makes more sense because we know this is y, this is x, this is theta, and then this is y, x. But in this case, y is actually sine theta, and x is cosine theta. And then this is just 1 because it's the unit circle. So now we have another line. This is also 1 because it's the radius of the circle. But we've changed the angle so that this angle can be represented as delta theta, right? The change in theta. Now, the point here, right, let's make that P, and the point here, the original point, is Q. To get from Q to P, there's a difference in the Y value and a difference in the X value, right? Okay. So what we're going to do in this proof is use first principles. If you don't know what first principles is, it's like the derivative of x equals the limit as h approaches 0. So h is just some value. So this is like the rate of change, rise over run formula that you're all familiar with, right? It's basically the same thing. H is just the difference between the 2 points you have. So in this case, h is like delta theta. It is, actually. So that's exactly what we're going to do. So we know the derivative of sine theta in terms of theta equals the limit as not h, but delta theta, rather, approaches 0. And then instead of the function with an input of x plus h, we're going to input sine of theta plus the change in theta. Because remember, this entire angle right here is theta plus the change in theta to get point P. And then we subtract sine of theta because that's just f of x. That's just the original function. And we divide that by the change in theta. Okay, now we simplify. Something important to note. Sine of theta plus the change in theta is just, so it's this angle, and then we're getting the sine of it. So it's basically just this length right here. And what is that length? If we look at what we've already defined, we can actually calculate the length. We can determine the length because it's just the addition of the change in y and y. Pretty simple. So we can sub that in, right? Because that represents sine of this angle, and hypotenuse is 1, so they're just equivalent. Again, we write the limit because we still have delta theta. So this is just y plus delta y, and then minus y, right? I said earlier, I think, that y is sine and then x is cos. So since y is just here, we're just subtracting. These cancel, giving us this equation. Delta y over delta theta with a limit of, delta theta approaching 0, because we can't divide by 0 in this case, because then it will be undefined. We have delta y. How do we get an equation so that we can rearrange for delta y and then sub it into this equation? Okay, let's draw a diagram. So in this case, this diagram is basically going to be the same thing with slight modifications. So rather than having a radius of 1, we're going to extend the radius beyond the circumference of the unit circle. And then we're going to still have the change in theta, right, up here. This is point P. This is like point Q. And then this is the change in y, change in x, right? We're going to make a chord from P to Q. So P to Q is a chord, and we're going to express the length as r. Okay, so remember, this is P and Q are on the circumference of the unit circle, so that's why P to Q is actually called a chord. Okay, so now something else we can add. We can add another horizontal line like or parallel to the x-axis, and then this angle will therefore still be theta, right? Because that's an angle rule. Two parallel lines and then a line going through them creates two equivalent angles. We're also going to add one final thing. So rather than just having theta, from this horizontal, we're going to have an angle that goes anti-clockwise, and that's going to be phi, right? So this angle is going to be phi. So this, from the horizontal, anti-clockwise to the chord PQ. Okay. So why does that help? Let's think about it. So I'm just going to draw this. That's essentially what's happening, right? Phi is going from the horizontal to this triangle, this right triangle, and that's what's happening. Yep. Okay, so something you will notice is that we can use what we have, like the given information, to rearrange for delta y. So in this case, sine is the correct trig ratio for this. So sine of this angle, which is the base or the acute angle of phi. But guess what? Sine of phi will still give you the same value as sine of this base angle. This base angle will be like 180 minus phi. In this case, we can actually use phi. Like, let's think about it. Okay, let's actually demonstrate it. So, actually, no, never mind. So, we know that this equals the opposite, which is delta y over hypotenuse, which is r in this case. So then we can multiply both sides with r to rearrange for delta y. Okay, now we can sub it in. Limit as delta theta approaches 0, r sine phi over the change in theta. Something to note. As r approach, or as delta theta approaches 0, this angle, r will approach 0 at basically the same rate. So this ratio would be 1. Let's actually demonstrate that. Okay. So we have this, right? We can actually demonstrate it using our calculator, right? So this is an isosceles triangle because both from the origin to P and origin to Q, the length of that would be 1 because they're both radii of the unit circle. Hence, it's an isosceles triangle. So then we can actually divide the isosceles triangle into 2 right-angled triangles. We can halve them. So then this would become delta theta over 2, right? We've halved the angle, we've drawn a line straight through, and then hence this would actually become r over 2, right? Half of r, because the base length, would be halved because we divided it, we bisected it by this line. However, this would still be 1 because it's, again, radii of the unit circle. We can use sine, right? Delta theta over 2 equals opposite over hypotenuse, which is just 1. Okay. Let's think about this. As delta theta approaches 0, what happens to r over 2, right? We've predicted that the ratio of r and theta over 2, delta theta is going to be basically 1 to 1, so the fraction is going to be just 1. Let's actually see if that's true. They're obviously going to decrease, right? As the angle decreases. So if I sub in 0.1, we get a small value. Okay, that makes sense. The angle is small, and we subbed in, and we get a small value in return. What about if we keep increasing it? Okay. What about more? Speed it up. What about even more? Okay, you'll notice that the calculator later, it's probably not exactly 0.000001. However, like rounding, that means that the calculator basically says it's very, it's approximately the same. The angle we input is equal to the value we get out. Let's see if that is not just a coincidence. Okay, what I meant was to sub in a value even smaller. We again get the same value. Okay, so we see a common trend as the angle we input, so delta theta over 2, decreases and approaches 0. Then this also approaches 0 at essentially the same rate. So then, if you were to divide these two, with each other, you'd get 1. Therefore, as delta theta approaches 0, r over 2 approaches 0, at the same rate, at approximately the same rate. Okay? Hence, r over delta theta is basically 1, right? Okay, so that means delta sine of theta over d theta, not delta, well, technically it is, this does represent delta. It's just we use d to represent it. Okay, so the derivative of sine theta in terms of theta is just sine of phi. Okay. How do we convert this in terms of theta? Right, right now it's in a different angle. Okay, so what can we use? We can use this diagram. We created before. Okay. Now, here, something interesting happens. Like we said, as delta theta approaches 0, this value gets marginally small. It approaches 0. R approaches 0. But what happens to P? P, remember this is on the circumference, so P would go like this in this arc. What would happen to the gradient though as this chord decreases? Essentially, once R becomes like almost 0, it's essentially a tangent to the unit circle, right? The chord, if you extend the chord outwards, it would basically represent a tangent to the unit circle. If it's a tangent to the unit circle, what happens? Well, then it's going to be perpendicular to the radius. But why? How do we know? Okay, let me demonstrate what the angle actually is, by the way. So, in this case, phi represents theta plus pi over 2. Now, you could obviously calculate this yourself, right? Based on the information I just gave. So, in this case, the reason for this equation is because we're aware that phi includes theta, right? That's a given. This is just what happens. But not only that, it extends further by a bit, and this amount depends on the change in theta. If change in theta is essentially 0, which we said earlier, this chord PQ becomes a tangent. If it's a tangent, and we know that the radius is essentially a normal to the circle, right? The angles between these two are 90 degrees. They're perpendicular to one another, so that means this angle is 90 degrees. So phi is just theta plus pi over 2 at when the difference is negligible. So then we can write that. We just sub in the value for phi. So we write theta plus pi over 2. How can we convert this to something that's just theta? Something interesting is we know that sine and cosine are complementary functions to one another. So this is in terms of that, yeah. So what we can do is this just equals cosine of theta. And that's your answer, right? And that's correct, right? That's what we know. We're aware of this formula. Let's think about this. I'll just draw a unit circle. Or no, not a unit circle. Okay. If I sub in theta equals 0, what happens? Sine of pi over 2 is up here, and it's 1, right? The value is 1. Okay. Like, this is based on a unit circle, by the way. It's not like the value this gives. Well, in this case, yeah, it is, but for the other ones, no. Okay, so what about if I sub in pi over 4? That becomes 3 pi over 4. It's somewhere over here. Yeah. What about negative pi over 4? It's going to be over here. But you'll notice that regardless, the values given would be positive. We know that these values, the y values here, they're positive, they're above the x-axis. So if we were to sub those values in for cosine theta, we should get the same values, and that's exactly what happens. Cosine theta of 0, cosine of 0 is just 1. Cosine of pi over 4 is going to be here. Negative pi over 4 is here. But guess what? Since cosine is related to the x-axis, it's going to be positive. Okay, so this is in line with what we expect. Now, something to note, it says on the syllabus dot point, right? Cosine, the derivative of cosine. You just essentially do the same thing, right? But in terms of x in this case. And then you'll notice that something changes. So I'll just do it quickly because I already have diagrams basically representing the same thing. So in this case, hopefully I'll be able to do this quicker, right? Because I basically said everything. This time we're after derivative of cosine theta in terms of theta, and this equals the limit as change in theta approaches 0, right? And we're after cosine of theta plus delta theta. You know, same kind of deal. Yeah, exactly the same thing we did for this, right? So the overall difference is just, so the overall angle is just that, you know, instead of cosine theta, instead of sine theta, it's cosine, right? Okay. However, there's a slight difference, you know, and you can kind of tell because we know that there's actually a negative if you derive cosine theta. And this actually demonstrates a negative. Okay, so let's recall. So instead of, you know, cosine of this, you know, just being x plus delta x, you'll notice that for this diagram, it's x minus delta x, right? And that's something interesting, something to know. Now, obviously, technically, delta x should account for that direction. But let's just say delta x is like the magnitude in this case. So this represents the magnitude. So then we're going to account for that by minusing the magnitude. Okay. Cosine of theta plus delta theta, right? It's just this entire angle equals adjacent, which is here. Adjacent is x minus delta x, right? It goes up here. It goes all the way here to the right, and then you actually go back a bit due to delta x. And then hypotenuse is just 1. Okay, so that's all we need to sub in. So I'll just go right hand side, and then left limit, you know, as it approaches 0, x minus delta x minus x, because cosine of theta is just x. You know, same kind of deal. These cancel out. Okay, and we're left with negative theta, negative delta x. Okay, same kind of deal, right? Exactly the same thing. Right. We're going to use this and determine delta x. Okay. So what I'm going to do, actually, no. Since we're not dealing with the magnitude, what I'm going to do is I'm actually going to keep it as positive. Right. I'm actually going to keep it as positive. Okay. So we're going to use this demonstration here. So what we're going to do is first state cosine of phi equals negative cosine pi minus phi, right? Because in this case, cosine actually changes sign, because by sign I don't mean like sign the trig identity, like the trig ratio, I mean sign like the positive negative. So since if it's over here, right, if it's beyond pi over 2, but if it's in the second quadrant, it's going to be negative because x is negative in that quadrant. You know, that's how you can think about it in terms of the unit circle. So we have to minus it if we want to convert it to the acute angle, which is what I did. So pi minus phi is essentially this angle right here, this acute angle. And that means we can use this right? So in this case, what does this equal? Well, we can put the negative to the left. Actually, no. We'll write cosine, we'll just write it again, but then instead, I'll use this, and I'll go off this. So negative cos of that. Okay, so what's the adjacent side? It's delta x, and then the hypotenuse is r. Okay, so then it just becomes r negative r cosine pi minus phi for delta x, right? And then we just sub that back in. So RHS, so right hand side, limit. Okay, so it's negative r cosine pi, like that. I don't know if this is correct. Not too sure. Okay. So all we can do, again, you know, as theta decreases, you know, same reason, we can just say cosine, the derivative of cosine theta equals negative cosine pi minus phi, right? We know that this is essentially 1, so we can just cancel them out. Cancel r and cancel delta theta out. We just get this. Now we need to convert phi into theta. Same thing, basically. So, given phi equals theta plus pi over 2, right? Same reason, you know, when the change in theta decreases, so that's almost 0, the chord PQ is essentially a tangent, you know, and then it's perpendicular to the radius, which if we extend it beyond the circle, we get this line, and then that's 90 degrees, blah, 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 right? Yeah, same thing. Okay, so what do? We just sub it in. Yeah, that's all we do. So then the angle inside, what does that become? Well, we'll go right hand side. Okay, so negative cosine of pi minus theta, phi, I mean, equals negative cosine pi minus theta minus pi over 2, right? Because the negative distributes to both. Okay. Now, you get negative cosine of pi over 2 minus theta. And again, since they're complementary, you get negative sine of theta. Bam. So therefore, this the derivative of cos theta is negative sine theta. Again, we can kind of use something double check that, right? So we have, if we sub in theta equals 0, okay, what do we get? It's negative cosine of pi over 2. Pi over 2 is just 0 for cos. And guess what? It's 0 for sine as well. Because the angle 0, there's no y value. The y value is 0. Okay. What about pi over 4? Okay, so it's going to be over here. It's going to be negative square root 2 over 2. Same thing. You know, pi over 4, negative square root 2 over 2. What about pi over 2? Then the angle here goes to negative, well, this expression part goes to negative cosine of 0. 0 for cosine. So cosine of 0 is 1, so it's negative 1. Okay, negative sine of pi over 2. Pi over 2, y is 1. It's going to be negative 1. Okay, so it adds up. So it's probably this. That's just a geometric proof. I don't know, geometric informal proof. It's likely not going to be on the exam tomorrow, but just in the off chance that, I don't know, like they decide to just put it in the exam, that's the whole reason why I just made this video. Of course, make sure to check the actual website, you know, in the description, because it's much more clear, but some steps aren't explained quite well, especially the part where you're using the limits to kind of simplify everything. That's something I noticed kind of confused me when I was reading it, but I hope that helps. Yeah. And good luck for the exams tomorrow.